Okay, so this example, I guess problem, this is problem number 1 on the fall 2018 exam number 3. And if we look at this, we have two 3-foot long shafts that are made of steel, and each has a diameter of 1.5 inches, and they are connected using gears fixed at their ends. Their other ends are attached to fixed supports at A, so they have a rigid attachment. They're not free to spin. They are also supported by bearings at C and D, which allow free rotation of the shafts along their axes. If a torque of 600 pound-feet is applied to the top gear, determine the maximum shear stress in each shaft. So we have some keywords in here that tell us whether we're looking at normal stress P over A or shear stress T rho over J. I mean, it's telling us we have a torque. It's telling us we need to find shear stress. Okay, we have gears. Okay, gears, we haven't seen anything with gears that's not torsion. Okay, so let's just go ahead and kind of get this set up. It's really nice that both of these shafts are they're the exact same thing in terms of material and in terms of geometry. It just simplifies everything. So if we look at this, they both have a length of 3 feet, which again, let's put everything in kips or inches or pounds and inches, just so that when we go back to work our problems, we have consistent units. So I just, from the get-go, I'm going to put everything in probably kips and inches. Okay. So I have the length is 36 inches. They each have a diameter of 1.5. That means my radius is 0.75 inches, and I know that the maximum is C. So I'm just going to go ahead and put that C is 0.75 inches, and that's for both of them. They're fixed at gears, blah, 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 but they are made of steel. And so if I'm looking back on my first sheet and I want to get material properties in, I don't really need any at this point because we're trying to find that shear stress. So we'll worry about G in just a minute in case we need it. Okay, so I have what I'm starting with. I know that I want to find shear stress is TC over J, and I have the thing, so J is going to be pi over 2 times 0.75 inches to the fourth, and that's in correct units. Okay, so I have everything but that magical torque. So now we have to start with, like we do everything, equilibrium. And if we start with equilibrium, then we are going to have to take this apart, because there's actually, as I'm twisting this, there's a resisting force that's acting in between these. And if I look at this system, if this is fixed over here at the wall and fixed at the wall, I have a torque, and then I have stuff going on at the wall. So it's indeterminate, but I need to go ahead with the gears on there and find a relationship between this one and the top shaft and the bottom shaft. So if I take the top one apart, then I have this applied torque way out here of 600 pound-feet. So I have 600 pound-feet. And we're going to change that to inches per foot, because we've already decided that we want it in kip inches, and we're going to divide by 1,000. So we're just putting those up there for notes for right now. And I know that there's a gear that's acting, and something's going to be resisting at the wall. So back here at the wall, when I'm looking way back here at the back, I'm going to have this torque A at the wall, but I have to recognize that's really also the internal resisting torque from A to E. Okay, and I'm going to have this force that's trying to push on the other gear. Okay, and we have this radius, and it told us that our radius of the top one is 6 inches. So I have this force times 6 inches. Now this force is down here. We are also on this gear down here at the bottom, and we are pushing back equal and opposite. Hey Alden, come get your shoe. Meg's eating your shoe. Okay, so if this force is trying to push it backwards, then we can see that the torque at the wall has to be equal and opposite. And we have this shaft, so we have a resisting torque at the wall, B, but we can also recognize it's going to be that same resisting torque that's in that shaft because we don't have any other loads applied to that shaft. Okay, so if we start at the top here, if we start at the top, then I can sum my torques, and we can do this however you can do right hand rule. Just be consistent. So I'm going to use right hand rule. So if I'm coming back here, I'm going to start at the back and right hand rule positive. All of that has to equal 0. So I have torque at AE. Okay, and I'm going to come down the shaft minus 600 divided by 1,000, that gets us into pounds, times 12 over 1, that gets us to kip inches. Okay, and then I'm coming, I guess I changed it from right hand positive to going backwards. This direction is positive, positive, negative. So this force plus force times that radial distance of 6 inches equals 0. Okay? And we can simplify TAE minus, let me find my calculator. Here's the problem. I have my calculator and then I lay it down and then I kind of forget where I put it. Okay? So I have 600 divided by 1,000 times 12, and I get 7.2 kip inches. Okay, minus 7.2 kip inches plus 6F equals 0. And if I look at this bottom shaft, I'm also going to have some, equilibrium. And I'm going to do backwards right hand rule. I'm being really sloppy, but these are both positive in my head, okay? In that direction. So now I have a negative TBF plus F times 2 equals 0. So we can say 2F equals TBF. F equals TBF over 2. And we can plug that in back up here. And that way we have one equation that relates AE, BF, my torques in both of these shafts, and what's applied. Okay? So if I plug this back in, I'm going to get TAE. Here's my equilibrium equation, TAE, plus 6 over 2, okay, 6 over 2, 3 TBE equals 7.2 kip inches. Okay, so I kind of did some math in my head, but if I'm going to take this value and plug it in here, I'm going to have 6 over 2 is 3 TBF, TAE, and then moving that over equals 7.2 kip inches. So I can see that we are indeterminate, and I have my one equation from equilibrium, and now I'm going to have to go back to compatibility. And I have to remember that it's going to be a function of either radius or teeth. And if this is 6 inches and this is 2 inches, then as this twists over, okay, that angle, it's a function of how far it's going to twist. So it's dependent on that radius. So when I look at the compatibility on here, I know that the angle of twist from A to E, it's going to have that same twist from B to F, or a ratio thereof, because they are both connected and rotating together. Okay? So I'm going to have the rotation of E with respect to A, okay, has to somehow equal the rotation of F with respect to B. And the beauty of teeth, or a radius, or a diameter, is that you just take that value that's associated with each gear, and we went over in class where it came from, and we now have our ratio. Okay, so it's pretty easy peasy. So if I'm looking at this, I have 6 inches, and then, well, what is my angle of twist from E to A? I know that the angle of twist is TL over JG. So I'm going to have the torque, okay, that's from A to E. I'm going to have the length, the J, and the G equals 2 inches. The torque from B to F, length JG. And this, this is why I wait to put numbers in until I get started writing up my equation, because I may not even need numbers. I know they both have the same length. I know they are both the same material. And I know they both have the same diameter. So what I'm left with is 6 TAE equals 2 TBF. So TBF equals 3 TAE. And this is my second equation. It can go right back in here. Okay? So I have TAE plus 3 times, well, TBF is 3 TAE equals 7.2 kip inches. Okay, and these radius that we had were in inches, so we're still good on units. So I get 10 TAE equals 7.2 kip inches. So the torque in A to E has to be 0.72 kip inches. 0.72 kip inches. And if that is 0.72 kip inches, okay, if this is 0.72 kip inches, then TBF has to be, okay, we can go back up and we can either use this equation or we can use, where did it go? This equation. So if AE is 0.72 and I need to find BF, then I can take 7.2 minus 0.72 minus, and then divide it by 3, and I get 2.16 kip inches. So here's the torque in both of those members, okay, 0.72 and 2.16. So now I can go the shear stress in A to E is the torque, 0.72 kip inches, okay. Now I need rho, or C, that's my radius on the outside, pi over 2.75 to the fourth, and we're still looking at kips and inches, and I'm going to get a shear stress, okay. When I look at this, I'm going to get a shear stress of 1.09 KSI, and that's from A to E. I can do the same thing, and I can go from B to F. So I'm going to have 2.16 kip inches times 0.75. Remember, they're the same. Divided by pi over 2, 0.75 to the fourth. And if I multiply this out, I get 3.26 KSI. And that's the shear stress from B of F. Okay. And so the first thing then I would have to do here is I need to make sure that both of those are less than yield. Okay, both of those need to be less than yield. And depending on the steel, it could be 21 KSI. And both of these are clearly less than that value of yield, so it's a very valid solution.